Okay, here's my plan today. I want to present maybe like the simplest starting point for doing mathematical theory of neural networks in some kind of comprehensive way. It's sometimes called the infinite width limit. So I'll remind you exactly what I mean in a second, but we're going to take a random neural network. Actually, we'll also train it in the second half of the lecture, but we're going to fix the depth of the network. That was, remember, the number of layers. We're going to take the width to infinity. We're going to see what happens. Okay, so somehow the punchline is that in this particular regime, a lot of things simplify about neural networks, and you can really say a lot. And so here I go. But again, let me just say it's more mathematical today. So you should ask me more questions rather than less. I'm going to try to go slow, but sometimes I get too excited, so I can't help myself. Okay, and I made this division because I want to try to keep what's here on the board so we can have the notation. So we'll see how it goes. Okay, so what are we going to do? So for the first half of the lecture, also tell me if you can't read this. I'm going to write very slightly smaller so I can have more. But is that too small for you? From here?
As big? No, from here is better.
Oh, then what are you worried about? Let them complain. You know what I mean? Can people see this from the back? If you can see this from there, then they should be able to see it on the camera.
Here is very clear.
Good. Well, if you're on Zoom and you can't see it, you should like speak up now or forever hold your peace.
It's okay.
It's fine. Okay. If it becomes a problem, you should tell me. Okay. So let's consider a fully connected depth L network. Okay. So let me remind you what that means. So I'll write it in coordinates this time, or in components. So remember the notation was for each input x to the network, you process x through a bunch of layers, and this is a vector that you get after L plus 1 layers. And so when I write an I down here, that's like the ith component of this vector. Okay, and the recursive formula for this thing was like this. There were kind of two cases. So in the case where L is greater or equal to 1, what did we have? You had that this was just an affine transformation of the previous layer. So there was a bias. And then you sum on J goes from 1 up to NL over the previous hidden layer with WL plus 1 IJ. And you take sigma of ZLJ. Right, so this is what happened when L is greater or equal to 1. Oh my God, I'm going to squeeze it in. Okay, I'm going to write it over here. L is greater or equal to 1. Doesn't much matter, right? It's just you have a vector of activation at the previous layer, you apply sigma to it, you take a linear transformation. Very good, and something very slightly different happened in the first layer. You just didn't apply sigma. That's the only delay. Okay, it goes from 1 up to NL. Oops, this is N0. This is W1 IJ. And then you have just the Jth component of X. And this is when L equals 0. Right, so little n sub L was the width of the nth layer. That's how many neurons you had in the nth layer. So I runs from 1 up to NL plus 1. Let me write that in some other color, just so that, because I know there's a lot of notation. So I want to put it up at least. Okay, so here I goes from 1 up to n little L plus 1. That's the dimension of this vector. Okay, so this is how you make a neural network. You do this, and because I have depth capital L, I stop when little l is equal to capital L. The output is Z capital L plus 1. Okay, is that ringing a bell for people? Is that okay? Okay, fine. Okay, so what are we going to do in the first half of the lecture? We're going to start with neural networks at the start of training when the B's and W's are random. Okay, so we're going to consider this with random weights and biases. So let me tell you what the weights and biases are going to look like. Okay, so the weights, WL plus 1 IJ. So everything is going to be independent Gaussian. It's going to be very simple. Mean 0, variance CW over the previous hidden layer width. We'll see in a moment why that's important. They're all independent. And the biases, BLI, are also Gaussian. Mean 0, variance CB. Okay, so here CB and CW are some kind of fixed constants, which you get to choose, and we'll see that they're quite important, okay, a bit later. But for now, they're just fixed constants. Think of CW as being like 1 and CD is equal to 0, for example. That would be. Okay, so this is how neural networks start their lives, right? You fix the architecture of the network, in other words, the depth, the number of layers you have, and the widths, these dimensions of the intermediate vectors you have, and you randomly choose the B's and the W's. So you have random affine transformations. Okay, is this okay? Let me just not speed through this. I know it's a little overwhelming potentially in terms of all the indices, at least I get confused. Okay, so here's my goal for the first half of the lecture, at least. I want to explain to you, now I can tell you exactly what the infinite width limit is. Okay, you fix capital L, the number of layers that you have. That you take all the hidden layer widths, N1, N2, up to N capital L to infinity. That's what we're going to do. And we're going to study what happens both at the start of training and during optimization. Okay, but to do that, let me put a definition here because I'm going to erase it. So that we're kind of on the same page. So to state the main result, I'm going to put the main result here. And then I'll tell you some things I want to keep up here. That's my dream. Okay, so we'll see if I can fit it all in there. Okay, so just so that I have some notation, let me tell you how I write a Gaussian process. Okay, so given a function mu, Rn0 to R. So remember, N0 is the dimension of the space in which X lives. So the output of a neural network is a random function from Rn0 to R capital L, M capital L plus 1. Okay, so mu is going to be my mean function. And I have a positive definite covariance function. Okay, so it takes in two inputs, R, and it's a positive definite function. So what I'm going to write is I'm going to say a function f is distributed like a Gaussian process with mean mu and covariance function k. I'm sure most of you know this definition, but maybe not everybody. Okay, so this is just a definition. This is a way of making a random function from Rn0 to R. It's going to be a scalar valued random function. And it's the simplest kind of random function if and only if the distribution of f restricted to any finite collection of points is a Gaussian. Okay, so this has the distribution of a Gaussian with mean mu of x1 down to mu of xk. Okay, and the covariance matrix is k of xi, xj, with I and j going from 1 up to 10. Okay. I assume people know this definition, but my point is that I'm going to write a Gaussian process in this way. The first slot records the mean, the second slot records the covariance. Okay, so okay. Okay, all right. So in some sense, Gaussian processes are the simplest kind of random function that exists. And so it's amazing that neural networks behave like Gaussian processes. So that's theorem A. Theorem B later. So here's the result. So let me be very precise. So you fix the depth of the network, it's L. You fix the input dimension, and you fix the output dimension, and you fix the nonlinear function sigma that you have. Okay. Secretly, there are some assumptions on sigma. It's like polynomially bounded. Don't worry about it. It's not actually very important. Okay, like basically any sigma you like is okay. So then, here's what you get. Okay, so as you take all the hidden layer widths, N1 up to N capital L, you send them to infinity. You have a sequence of stochastic processes. You know, I fix the input dimension and the output dimension. So each choice of N1 up to N capital L gives me a random function from Rn0 to Rn L plus 1. And the law of these random functions just converges to a Gaussian process. Okay, so Z L plus 1 of dot, I'll write it this way. Okay, dot just means it's the whole function. It converges distribution to a Gaussian process. Okay, with mean 0 and a certain covariance function, which I'll write KL plus 1. So, okay, so let me put the exact formula and then I'll explain what this thing means. So remember, this is a random vector, the output, right? There are NL plus 1 output components. So what I mean by this, I'm going to write this out in just a second, is that each of the components is independent of all the others. So actually, every component is just an independent copy of the same scalar Gaussian process. Okay, and I'm about to tell you how to think about KL plus 1. So here I go. So IE. So what the heck do I mean by this? Okay, so the fact that the mean goes to 0 just says that if you were to take any component of the z's and evaluate it at any x you like, the mean converges to 0. Okay, actually the mean is 0 at every width just by symmetry, but that doesn't much matter. So that's what the 0 means. And then the whole thing is Gaussian, so I have to tell you the covariance structure. Okay, so I need to tell you the covariance between CL plus 1 I of x and the L plus 1 J of x prime. Right, like if it's a Gaussian, I have to tell you the mean and the covariance. And I have to be able to evaluate at any two inputs I like and take any components I like. Okay, so what do I get? What I mean by this notation is this converges to, so you get a delta function on I and J. In other words, the different components are independent of each other. And otherwise, you evaluate at KL plus 1, evaluated at x prime. Okay, so KL plus 1 is a particular function I'm about to describe. But this is like what I mean by this notation. Okay, so before I tell you the recurrence in L that K satisfies, is this clear what I'm saying? Like it's it's kind of heavy at the start because I want to state the formal theorem, so I have to like say something precise. But precise things are brutal. They're not my favorite, but it's a math seminar, so you have to do it. Yeah, there are questions about this. Is this okay? How do you feel about it? You're happy. Well, if you're happy, okay, and maybe happy. I'm probably happy. Okay, so this is part 1 of the theorem, that in the infinite width limit, in this precise sense, the distribution of the random function you get at the output is a Gaussian process. But moreover, you actually get a nice formula for the covariance function. Okay, the formula looks like this. So in fact, the covariance function after L plus 1 layers, evaluated at 2 inputs. I usually put Greek indices on my inputs. So x alpha and x beta are 2 different points at which you can study this thing. Has this nice exact formula. So it's CB, it's the variance of the biases, plus CW, the variance of the weights, okay, times the expectation with respect to the previous Gaussian process. That's what the subscript KL means. And what you do is you take sigma, your nonlinearity, and you take ZL1 of x alpha, and you take ZL1 of x beta. And to close my bracket. Okay, so the way you should think about this is it tells you that the covariance function you have from L plus 1 layers of nonlinearities satisfies a nonlinear recursion in L, which is determined by the covariance you had after L layers and the nonlinearity you had and the weight and bias variances. Those are all the things that went in to determine your problem. So of course they appear somehow. It'd be crazy if they did. Okay, and K, so and then maybe just for completeness, K1 of x alpha, x beta. Like the initial condition for this recursion is very simple. It's just CB plus CW times the dot product of x alpha and x beta divided by the input. Okay, it's just a Euclidean looking. Okay, that's the start for the recursion. So I told you the initial condition. I told you how to go. In principle, I told you everything. Okay, so that's the end of the theorem. So okay, let me again pause. I'll just let people digest for a second. Ironically, the notation is going to get easier rather than harder, I think. But there's kind of a lot of stuff.
CBs and CWs in principle could depend on the layer, right?
They could.
Wouldn't change anything.
No, it would not. Correct. Correct. Sometimes they do, but I take them not to in space. That's right.
Is there any special value of the parameters for which this covariance gets, like an analytic form, like power? For instance, if you take CB equal to 0 and CW equal to 1, and then this has some.
Okay, so indeed, so I'm going to talk about this because it's important both in theory and in practice. But it turns out that there is basically a unique way to set CB and CW depending on your nonlinearity sigma, so that your covariance functions are neither exponentially growing nor exponentially decaying in L. You think of this kind of like as a dynamical system, and you have to fine tune the parameters. So your fixed points are actually critical fixed points rather than generic fixed points. And so the values of CB and CW will depend on sigma, and that's like an important thing. If in practice you don't set them in the right way, you can't train your networks. So yes, there are good values, and I'll explain how to get to them. But that's like its own whole thing. Other questions or comments? Is okay. Statement. It's just a statement. Not too bad. Fine. So here's my goal. Okay, maybe you'll like the goal, maybe you won't. My goal is to prove the theorem. Okay. Moreover, my goal is to prove the theorem before the break. Okay. So you might say it's a disaster, but okay, I claim the proof is trivial, or at least I'm going to hide all the difficulty. That's actually the truth, right? I told you last time I'm kind of a liar. So here's going to be my plan for the rest of kind of the first half. I'm going to tell you the philosophy in general of what are the most important properties of a random neural network? How do you study such an object? And then once I tell you the philosophy, this theorem is actually very easy once you basically know the important structure theorems about random neural networks, okay? So I'm going to put here the structure of random neural networks. See, okay, so how do you study such an object? Okay, so the most important thing in studying such an object is not to try to compute everything all at once. That mistake has been made by many people, and it's a disaster. Okay, but there's only really 2 or 3 structural properties that are important. Okay, so the first structural property is like this: neural networks are Markov chains. Okay, so in what sense? Well, this sequence of fields, CL dot, with respect to L, right, is a Markov chain. Surely, if I give you what happens after little L layers, you don't need to know what happened before to determine what happens after deeper in the network. Okay, that's extremely important structure. And so whenever you have a Markov chain, what do? You analyze the transition probabilities for one step of the Markov chain. That's, of course, the game you play. So in fact, the transition probabilities are very simple. And they're extremely simple, especially if you take the weights and biases to be exactly Gaussian like we do. Okay, so here's the basic observation. If I give you the vector of activations CL, I give you this field, then the next layer is simply Gaussian. It's exactly Gaussian without having to do anything. Okay, so then this map, the field X maps to ZL plus 1 of X, okay, is Gaussian. Okay, it's Gaussian with what parameters? And with mean 0. Mean 0. Okay, so I mean, you can just see that. That's why I wanted this formula. We're going to use this formula a lot. You see, if I give you Z little l, then these things here are just constant, right? Let me underline them somehow. Right? Like these are some complicated functions of x, but I'm saying these guys are just constant. Well, if that thing is constant, then of course each of the components of ZL plus 1 is independent because the different weights are independent. And it's Gaussian, it's just the sum of a bunch of Gaussians. So it's that simple. Okay, it has mean 0 because all the Gaussians have mean 0. Okay, and it has a simple variance, right? And so I'm going to write k hat L plus 1 of x alpha and x beta for the variance of this thing, okay, the conditional covariance. So it's the covariance of Z L plus 1 I of x alpha with Z L plus 1 I of x beta given CL. Okay, it's a trivial thing to do. It's just a bunch of Gaussians. You compute the covariance, and what do you get? Okay, well, the B's have to pair with the B's, right? You just get the sum of the variances because everything's independent. So you get the variance of the B's, plus you get the variance of the W's times the sum of the squares of the things that multiply the W's. In other words, you get sigma of Z L J of x alpha times sigma of, what did I do? This is yeah, sigma of Z L J. My mind froze for just a moment.
Sorry, the subscript is J, maybe?
Thank you.
Okay.
That's what happens when you're talking, right? Okay, just some of the variances of this thing. The variance of this is CB. The variance of this is the covariance of this between the two things is the CW over NL, and you get this times the other one, you know, with X alpha. That's simple. Okay, so that's the that's very important. The conditional transition probabilities for one layer to the next are very easy. Everything's actually IID Gaussian. But of course, the issue is that, okay, you can think of it like this. The components of ZL plus 1 of this vector, they're Gaussian, but with a random variance. You can think of it like that, right? This object is actually random because these components, CLJ of X alpha and CLJ of X beta, are themselves random. So, okay, if you have a Gaussian with a random variance, it's not a Gaussian. Okay, so that's why at finite width, these networks are not Gaussian. Okay, but so very good. Now, like, what do you notice? And maybe this is a good place to ask the audience. You already know I like to ask the audience, and even if people don't want to answer, I'm still going to ask. What do you notice about the structure of this variance that makes you happy? If you just had enough cups of coffee today and you're following along, something should make you very happy about the structure of that variance. I'll erase while you think. And it sounds hopeless. Sounds hopeless. Each of these z's is neither independent nor Gaussian by itself. They're all correlated somehow. I'm taking some crazy, sounds like I did nothing. But I actually did something great. Okay, I did something. Let me not say something great. Anything? What do you notice? Maybe a student can answer. Maybe if you're just a student at heart, you can answer. Okay, so here's the key thing. So this is point number 3. And I'll put it up there. Unfortunately, I failed to fit everything in. So point number 3 is that this conditional covariance has a very special structure. Its structure is that it's an average of things at the previous layer. Okay, so I call it collective observable. So what I'm saying is the entries of this covariance function, or covariance matrix, if you want to think of it that way. So these are examples of collective observables. Call them collective observables. Okay, so in other words, by definition, a collective observable at layer L takes in a function f, then by definition, it's 1 over NL times the average over neurons. I guess I put a J here, so I'm going to put a J here as well. In that layer of your function f, applied to the finite dimensional distributions of the field. Okay, X alpha. I'll write it like this. Alpha is 1. Okay, that's terrible, but 1 up to L. Right now. Okay, it's just an average of the same function applied to these random variables. Now, these random variables are not independent, but they're identically distributed just by symmetry. So this is like a very special structure. And the reason this structure arises is that the network was fully connected. You see, you have a perfect symmetry in all the W's. Like the number of the neurons don't mean anything. You can always symmetrize. And so, of course, it's only averages over the neurons that can ever enter anything you write down. Okay, does that make sense? People agree with this statement? Okay, so here's the difficult thing, which I'm going to sweep under the rug. Or more precisely, I'm going to state it but not prove it. Okay, so here's like a proposition or a theorem, really. It's like not such an easy calculation. So the proposition is like this. So these are averages of random variables which are identically distributed but not independent. However, they concentrate around their means as if they were independent. Okay, that's what I'm about to write down. The proposition goes like this. So the mean of these collective observables, if you give any f, any L, okay, f has to be polynomially bounded. I'm not even going to write it. Maybe I will write it. Fine, I'll write it myself. So f is polynomially bounded. That's the kind of restriction you need on f. So these are order of n to the 0. Let me write it that way. In other words, they don't blow up as you send the hidden layer widths to infinity. Okay, they're uniformly bounded in n. That's my slightly loose notation. And the second thing is, if you center them and take a product, so I take the product, let's say a few of them, and I take any f's that I want, and I subtract the means of these things. Okay, this looks like big O of n to the minus q over 2. Okay, that's how they go to zero as n goes to infinity. And this is exactly the moment, the rate at which the moments should go to zero if you just had an average of IID centered random variables. Okay, that's what I mean by they behave as if they were centered. Sorry, as if they were independent.
And it's NL, right?
Yeah, right, so you should think of n as the minimum of n1. And now, you want to be very small. Yeah, I'm setting all the hidden layers to infinity. And so either think of them as all equal to n, or take n to be the minimum. So these are all asymptotic statements, right? This theorem is all about taking all the hidden layer widths to infinity. So that's the regime in which I'm in.
The intuition is a computation of moments, or these are not independent but satisfy some mixing conditions or something?
So unfortunately, the intuition is harder than that. It turns out the only way I know how to prove this is you first prove that you first study their cumulants instead of the centered moments. For every cumulant, every joint cumulant of any collection of these things, you prove the right bounds on the cumulants, and then you use the cumulants to bound the moments. And for the cumulants, you have to do it recursively in L. So it's like, it's not so easy. It's like the hardest thing in the paper that I'm talking about, basically. And I could go into it, but that's like, it's very technical. I don't think it's a good thing to do. It's already technical enough, you know. So fine. Okay, so I'm gonna black box this. I'm simply going to use this. I'm gonna try not to erase what came before. I almost managed to fit it in the left side. Okay, so my goal now is I claim with these two observations and with this estimate, which I haven't really shown you, it's now easy to prove that neural networks become Gaussian processes. Okay, I'm gonna basically fit the proof. I might not even have to erase anything in the proof. I think I can just do the proof from here to there. Just gonna move here, right? Okay, but let me just pause because this is kind of like, I felt like I wanted to do the setup first. So that the proof could at least not be like fourthly elongated. Okay, so are there comments or questions about this? We have lots of time, so.
The fundamental thing is that for a given layer, the Wij are IID, right?
That's right. So it's not that important that things are Gaussian. It helps a little bit because then you get a sum of Gaussians and things are exactly Gaussian. But you see here, like, if the W's and B's weren't Gaussian, but if NL is big, you just take a sum of a bunch of independent things. So it's just close to Gaussian. But yeah, fundamentally, the important thing is that the W's are all independent. And therefore, conditional on the previous layer, the next layer is exactly independent Gaussians in each.
So not even IID for a given layer, for a given small L, for example.
So, well, yes, I think I'm missing the question.
Fix small L.
Yeah,
I'm saying Wij.
Yeah, I'm saying condition on the sigma algebra of all the things up to layer little l, up to and including. In other words, this thing becomes measurable. It's now just deterministic. Then the next layer, condition on that, is just exactly Gaussian. It's just given constants times a bunch of Gaussians.
Yeah, no, this is.
Yeah.
Yeah.
So
I was wondering to generalize the W's that are here. They are all IID.
yeah, they're all,
everywhere.
yes.
But what you really need is IID for a given layer. And not even Gaussian.
That's true. So, okay, so I wrote a paper where I was a bit masochistic, I have to be honest, but I proved the universality result. This is true for any W's that just have some moments. And
But then morally, what is special about, the neural network, so that even if they are dependent, you have a large numbers, it's like the components are exchangeable in some sense. I mean, I understand the argument about the cumulants, but is there some just
No, no,
dependence of the weights?
No, what's special is the following, right? If you take an n by n random matrix and you hit it with two different vectors, the results are almost independent of each other. You see, each layer is you have a big random matrix of weights, but you hit it with just one vector. So the different components are almost independent of each other. Right? Their dependence is like 1 over n. And that's secretly why they're weakly correlated. That's kind of all you're using, you know.
Yeah, so it's, yeah, because you it as a, even as a property of random matrices in some sense.
Precisely. That's all it really is. You could certainly state all this with just generic random matrices. Other questions? So let me explain the proof. So the proof, how do you prove convergence in distribution? Okay, there are many ways, but the way, so I won't explain how to prove tightness. Okay, that's an exercise to the reader, so to speak. But let me just show convergence of the finite dimensional distributions. Okay, and I'll do that by using Levy's theorem. Okay, so in other words, here's what I'm going to do. I'm going to fix a collection of inputs. I'm going to call them X capital A. So this is a collection of X alpha. Okay, alpha is in some finite set capital A, and the X alphas are just inputs in Rn0. And I'm going to study the distribution of the output of my network at these points. That's like the finite dimensional distribution of what you have. Okay, so let me introduce a kind of simple notation for it. Okay, so I'm going to write Z L I evaluated at this collection of points XA for exactly what you think. It's the vector Z L I of X alpha for alpha in A. Okay, so when I write my some neuron somewhere in the network evaluated at a collection of points, I just mean exactly what you think I mean. Okay, so what are you supposed to do? Okay, so by Levy's theorem, you're supposed to compute the characteristic function. Okay, so here's what I'm going to do. So by Levy's theorem, to show convergence and distribution, okay, you just need to show what? I need to show that the characteristic function of a random variable like this converges to the characteristic function of a bunch of independent Gaussians. Right, that's the game. Okay, very good. So let me do it. So here's what I need to show. I need to show the limit as the hidden layer widths n1 up to n capital L go to infinity. So I'm going to give this thing a name. So excuse me for a moment. I'm going to call it chi subcapital A of C. So I'm actually put the layer index here too. Capital L plus 1 for C. Sorry, I'll define this in just a second, but let me say what it's supposed to be equal to. This is going to be the characteristic function of a sum of independent Gaussians. So it's the sum, it goes from 1 up to n L plus 1. Sorry, give me a second to write the notation. Psi m transpose k L plus 1 sub k psi m. Okay, so where what? I'm going to finish writing, I apologize, and then I will take questions if people have them. Okay, so first of all, this chi L plus 1a is, of course, just, I didn't write it correctly in my notes, not the exponential. It's just the thing that you need to get the characteristic function. So it's minus I sum when m goes from 1 and L plus 1 psi m dotted with ZL plus 1 m of times a. Okay, so this is xi. This is just the characteristic function, or its expectation is the characteristic function of the joint distribution of these random variables, where I look over all neurons in the output of the network. Okay, and I've written, of course, psi just as a shorthand for all these xi1, the psi, and L plus 1. Okay, so let me just pause for a second and ask if it's clear what I'm trying to show. Okay, I'm just writing down the characteristic function of all the random variables I get at the output layer. These are these things. I introduce a dual vector for each one of them, right? This is a vector whose dimension is the number of points at which I evaluate. And then, okay, so this is the joint characteristic function of all of them together, because I just adopt one and I sum them up. And I need it to be the characteristic function of a bunch of independent Gaussians, right? And the characteristic function of a bunch of independent Gaussians is e to the minus 1/2 quadratic. Right? That's kind of all it is. So So let me pause. Is this okay? It's like, I feel like it's getting technical, but I don't know what to do. I don't know, it's like the simplest proof I know. But I really wanted to do a proof. You know, I was always told you have to do at least one honest proof. Math thought. And you have to do a joke, I was also told. And the key point is the joke and the proof have to be different. Okay. So fine, that was my joke. Okay, so now let me explain how to compute the characteristic function. It's going to be really easy. The proof is honestly almost done. Okay, so what's the point? The philosophy is always like this, because it's a Markov chain. We're going to condition on the previous layer. We're going to use that everything is Gaussian. And then we're going to write everything in terms of these collective observables and declare victory. Okay, I think I can actually fit the proof in here. So we're about to check. So what do we have? Right, so I need to compute the expectation of the characteristic function, okay, after capital L plus 1 layers evaluated at psi. Right, and I have to just check pointwise convergence of the characteristic functions for every dual variable psi. Okay, so what do I get? So I'm going to write it like this. Right, it's going to be the expectation of the conditional expectation. Right, I have to do my one-step analysis. Right, this is what I was taught. The first year undergraduate, always do a one-step analysis, because otherwise you will be stuck. Okay, so I'm going to condition on the previous layer, and then I'm going to integrate out. So now what do we know? We know that if you condition on the previous layer, every one of these things here, right, every neuron in the output, all of these, are independent Gaussians with mean 0. And the only difference is that their covariance is not k, but k hat. Right, this is the conditional covariance they have. I wrote it down for you over here. Okay, so therefore you also know their characteristic function. Okay, you just get the expectation of x of minus a half. You get the sum of I goes from 1 up to m, and you get psi m transpose k hat L plus 1 a psi m. Oh, look, that wasn't too bad. Right, like conditional on this thing, they're all independent Gaussians, and their characteristic function is exactly that of a bunch of independent Gaussians. The only difference is that their covariance is random. Here, the covariance was deterministic. So that this outer expectation is over the randomness that goes into the conditional covariance. Right, it's the randomness that knows about all the previous sigmas and z's and all of them. Okay, I'm going to pause because now you should be able to complete the proof yourself. That, or I have not done a very good job explaining what's happening. So I want to wait and see if someone can tell me what I should say. What are the magic words that allow me to replace the k hat L plus 1 just by KL plus 1 without the hat? I only gave you one result to use. This seems like a good result. So what should I do? So I'm going to give this result a name. Call it down. Right. So what does this proposition actually say? It says that the mean remains order 1, and for example, that the variance goes to 0 of any collective observable. Right. So in other words, I mean, that's why I call them collective observables. Okay, statistical physics people call them order parameters, whatever. It's all kind of the same. Right. So here's the point. So pound implies that if you take k hat L plus 1, okay, at x alpha, x beta, in other words, you take any component of this covariance matrix, which is random, okay, it converges in distribution to like its mean, to the limit as n1 up to nl goes to infinity of the expectation. It just concentrates around its mean. Plus 1 of x alpha, x beta. Okay, which I'm simply going to define for the moment to be k without the hat. Right, the variance goes to 0, therefore the limit of this thing is in distribution just the limit of its means. The means don't go off to infinity, the variance goes to 0. Okay, the random variable has nothing to do other than concentrate around some finite value. Okay, so nice. I know this. Now, question for you. So this matrix here, K hat, it's a nice positive semi-definite matrix. It's some covariance matrix. So the map that takes K to this expectation or to this X here is a nice bounded continuous function. Right? So the map that takes a positive semi-definite matrix K into X of -1/2 a sum on I goes from 1 up to M, Cm transpose K Cm is a bounded and continuous function. Right? It's bounded because K is positive semi-definite. So this thing is positive, but I have the minus here, and it's clearly continuous. And so since you have convergence and distribution of each entry of K hat, okay, you have convergence and distribution of the whole matrix. And so you can just replace K hat by its mean. Okay, so therefore, what do you find? You get that the limit as n1 up to nl goes to infinity of the characteristic function that you had, IA. Oh my God, so much notation. I apologize, but I don't know what to do. Okay, you just get to replace K hat by its mean, by its limit. Very good. That's exactly what you want. Okay, so there's no more expectation. I have an X minus a half. Sum on I goes from 1 up to M. Cm. Oops. Oh my God. Oh my God. I didn't put the right M's. And L plus 1. I apologize. What a disaster. Okay, M goes from 1 up to N L plus 1. Cm transpose K L plus 1 times Cm. Okay, very good. So, okay, so we just did it. We just proved that the characteristic function of the output, or more precisely, you take the finite dimensional distributions of the output and you take the characteristic function, converges to that of independent Gaussians. Okay, it wasn't so bad. Now, the only part of the theorem that's left is I need to tell you how to derive this recursion. Okay, the recursion is almost trivial, and I am almost out of time. So that's perfect. So let me just pause for 1 second before I do the recursion, because I think I can fit it right here, and my dream will be complete. And ask for comments or questions. I know it's kind of very dense, but it's like really the shortest, most transparent proof I know. I disagree with the word transparent, but everything's relevant. Questions, comments? I'm gonna pick on you, Domenico. How do you feel about the proof? You're happy.
You could also claim, use like Lutsky theorem because it's actually convergent probability.
That's true. That's true. You're correct. But let me also say that you don't need the full power of this in order to get convergence and probability or distribution or whatever. You just need that the variance is a little over 1. That the cheap version of that is actually really easy to derive by hand by like induction on L. If you want the real estimates, I'm going to need those estimates tomorrow. Then, okay, you have to work because that's the right answer. These are sharp. Okay, but I want a question or a comment from someone else. Wait.
So if you just send n L with large L to infinity and not the previous ones, would you get still a Gaussian process but with a less explicit covariance function?
Yeah, I'm thinking. No, he would not. So the issue is that you can apply this argument, but you will in fact not have that K hat L plus 1 converges in distribution to a constant. It's going to converge to some random variable. So you'll have like a Gaussian process with a random variance, which is not really a Gaussian process, something else. So at least I don't believe it's going to be true. So like people have studied these kind of things. People really use this in practice. What they do is they take a bunch of hidden layer widths to infinity, and then maybe they have one hidden layer width that doesn't go to infinity, and then they take a bunch to infinity and they ask what happens. And you don't get a Gaussian process. That bottleneck thing really like correlates things too much. And you get an interesting answer, you can write something down about it, but it's not Gaussian. It's what they call a deep Gaussian process. It's just words. Other comments or questions? Okay, so let me finish and then I'll take a break so people can escape if they don't like the mathematical rigor. Although the second half is actually going to be less technical. I'm going to tell you about how to do optimization, right? The first half is all about initialization. This is the start of training. And then I won't really prove all the theorems in the second half because they take too long to prove. But I'll draw some pictures and I'll tell you what the NTK is and okay, why. But I'm going to get there. Okay, so now let's derive the recursion for the covariance. It's fun. You can do it. Okay, so this is the limit, and n1 up to nl goes to infinity. So, right, our definition is it was this thing. So the expectation of, I'm just going to plug in my formula for k hat. So k hat is over here, this thing, right? And now all of the components, j goes from 1 up to nl, have the same distribution. So when you take the mean, the sum cancels with the denominator. You just get the mean of what? Okay, so I'm just going to, okay, well, fine. All right, this way. So I'm just going to write what I said. Get ZL1 of X alpha, sigma of ZL1 of X beta. Right? Not too bad. I just plugged in the definition. This was, by definition, the limit of the mean of the k hats. The k hats I had a formula for, so I plugged them in and I used that all of the indices 1 up to n capital L gave the same. Okay, very nice. So what do you get? So now this is CB plus CW. And now you see this thing in the end here no longer depends on n capital L. So I get the limit of n1 up to n capital L minus 1 goes to infinity of this expectation, sigma CL1 of X alpha, sigma of CL1 of X beta. Very nice. But now you see, we already proved, that's what we just finished doing, that as the previous hidden layer widths go to infinity, this converges to a Gaussian process, with the covariance being the covariance that I defined at the previous layer. So this just by definition, okay, sigma is a polynomially bounded function, whatever limit theorem you want. This is going to converge to the same as just replacing this by the limiting distribution. So you get CW, and then you get the expectation with respect to K capital L of sigma of the C L1 of X alpha, sigma of C L1 of X beta. Okay, that was the claim conversion. It's that simple. Not too bad. Not too bad. Okay, so that's it. That's really the end of the proof. I did everything. Okay, modulo, like digesting notation, except for proving this proposition, which I have to do to get a paper instead of just a blackboard. Okay, so let me just pause again and ask if there are comments or questions about the proof.
Just forgot divided by NL. In the, should we get divided by NL? C of W divided by NL.
Oh yeah, so I did that too quickly. You're right. So you have to take the mean of this thing.
Huh?
But you see each of the terms here, each of the j's has the same distribution just by symmetry. So when you take the mean of the average, you just get the average of the first term. So I skipped a step because I wanted to fit it, but you're totally right. So that's somehow the point, you know, like the mean of this collective observable is just, of course, the mean of any one piece of it just by symmetry. And so somehow we went from things at layer L plus 1 back to things at layer L. Like, yeah, doing very well. Nice. Other questions or comments? Okay, here's what I propose. I, in the second half, will erase all of this stuff, but I will keep. No, I'm just going to keep only this. Okay. I'll erase everything else. And I'll tell you a completely independent story about how to think about optimization of neural networks. Here I just told you about initialization. And I won't prove the results very rigorously for the second part, but I'll draw some pictures and give you a sense of why they're true. And I'm gonna wait, let's go 5-minute break until 3 o'clock. So I'll be here if people want to ask more questions about this before I erase it. Okay, okay. In the first half of the lecture, we saw something which when I first saw it, I thought was cool. Okay, like random neural networks are very complicated looking objects. But in this infinite width limit, they're actually the simplest kind of random functions you can have. They're Gaussian processes. Okay, but now I want to tell you not only about the behavior at the start of training, but I want to tell you exactly what training does. Okay, so in this particular infinite width limit, actually training becomes really trivial as well. Now I'm going to state the theorem, and then I'm not going to give you really the proof of the theorem. I'll give you some ideas, but I'm going to try to draw a bunch of pictures. And really, there's like at least 1 million papers written about this now. So like this is where a lot of math of neural networks stuff is happening or happened in the last couple of years. Okay, so let me state the theorem about how optimization looks like for infinite width networks. Okay, so let me give a couple of attributions. I did pretty good attributions in my notes, I think. But okay, so there's a paper of Du et al., which was very influential. Then there's a paper of Jacob et al., and there's some papers of Belkin. Okay, it doesn't matter. If you're interested in the references, there's many people who've done many things. You should ask me. I know most of them. Okay, so here's the theorem. So I'll be very careful, at least in the statement. So we're going to fix the depth of the network again. We're going to fix the input dimension. We're going to fix the output dimension, and we're going to fix the nonlinearity. Okay, and then what we're going to do is, remember, to do optimization, we need a function we're trying to minimize, right? What I told you last time is you are going to try to fit some training data using your neural network. So I'm going to define this function, script L of theta. So theta is going to be the weights and biases of the network. So it's all of these W's and V's, which I smartly have not erased. And it just looks like this. Okay, it's going to be the sum on I goes from 1 up to some number M. That's going to be the number of training examples. And it's going to be the output on the I input, with parameters theta minus yi squared. Okay, and you can think of these xi and yi either as just given to you by God, so to speak, or you can think of them as drawn IID from some fixed distribution or whatever your favorite model is for data. Okay, I'm only going to be talking about optimization. I'm not going to be talking, at least for the moment, about generalization, how well you do in predicting new things. And so if you only talk about optimization, just think of xi and yi as given. Okay, so what kind of optimization are we going to do? Well, we're going to do exactly what I said before, or some version of it. We're going to initialize exactly like we did in the first half of the lecture. The W's and B's are random. And we're going to do gradient descent, or really I'm going to do the infinitesimal version of gradient descent. I'll do gradient flow. Okay, so we fix this loss, and we consider optimization like this. Okay, so d by dt of theta at time t. Okay, so now the vector of parameters is what you're going to try to update. Okay, is equal to minus the gradient with respect to theta of the loss at theta t. Okay, so with the initial condition theta 0 as before. So really what we studied was just the starting point for optimization. Okay, when I say as before, I mean, let's say independent Gaussian with the variances there. Okay, so all the results I state also work if you do actual gradient descent, where you do the kind of Euler approximation to this with sufficiently small step sizes. But let me just focus on this. Okay, this is a method to try to minimize the function L, which is what training typically does. Okay, so here's the theorem. So then, as n1 up to nl goes to infinity. So again, we're going to be kind of in the strict infinite width limit, if you want to put it that way. Okay, so okay, actually, let me say it this way. Sorry, my notes say it slightly differently. I'm going to be slightly more quantitative. So these have to be sufficiently large. They're basically going to go to infinity. So how big do they have to be? They have to be polynomially big in the number of training data points you have. Think of like the number of training data points to the 10th power. That's how wide I need my network to be. Okay, so here's what I'm going to get. Then okay, so if this, so with my probability, So what's random here? Okay, really, there's maybe two things that are random. Your choices of xi's and yi's, think of those as basically fixed. But the initialization is random. So really, it's going to be with high probability over the choice of the starting point. We're going to have a couple of things that happen. And so thing number one is
High probability, it's like exponentially close to one as n grows.
you could make it exponentially close. It'll just affect some constants, which I won't even really tell you about essentially. But yeah, I mean, yeah, let me not get more precise. I'm sorry. It's not going to be relevant for really what I say. And I can state the theorem exactly for you if you want. It'll just be like how high the probability you want is going to influence the constant you have in this polynomial. So if you want it to be exponentially good, you have to. So the first thing is the limit as t goes to infinity of your loss at theta t, right? You're ultimately just trying to minimize the loss function. That was the game you're playing. K is equal to 0. So you actually succeed in optimization. That's the first thing. Remember, I told you last time, one of the big questions was, why does non-convex optimization work? And I'm saying in the infinite width limit, we can prove that it always works, or works with high probability. Okay, I'm going to state a couple of more things which are going to make clear why it works. Okay, so point number 2, and in some sense, this is the key point, which I'll spend a bunch of time explaining how this could possibly be true. You have estimates that look like this. If you look at the soup over all times, so we're going to track the full trajectory of optimization. Okay, so the actual trajectory of optimization you get, this actual theta t, defined by the really nonlinear gradient flow with the neural network, blah, 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 is very close to an object that I'll call theta t linear. Okay, so this soup is like O of n to the minus gamma. Okay, so n is like, again, the minimum of the widths, and gamma is a positive constant. It depends on exactly what you want, which number you get. Just think of gamma as being like a half. Fine. Okay, so I have to tell you what lin means. Okay, so I'm going to do it in the most cumbersome possible way. I apologize because I want to be very clear about this. Okay, so first of all, the linearized theta is just the solutions to gradient flow for a linearized loss. This is minus the gradient with respect to theta of a linearized loss at theta t ln. Okay, so that's not very helpful yet because I haven't told you what L ln is, but okay, that's what the other brackets are for. Okay, so L ln of theta is still not going to be that useful, but it's like, you know, the Russian matryoshka dolls. Okay, I promise they're going to stop at some point. So it's going to be the linearized neural network. I'll just write it like this: Z L plus 1 linearized at xi and theta minus yi squared. Okay, so the linearized loss is just the same loss on the linearized network. Okay, where finally I can tell you what the linearization is. You linearize the model itself. So this evaluated at x and theta is like this. You just do the Taylor expansion of theta around the starting point. Okay, you get ZL plus 1 of x and theta 0 plus, okay, you get the gradient with respect to theta of ZL plus 1 of x and theta 0 times theta minus theta 0. That's it. You truncate the series at first order. Okay, so let me try to explain what the heck is going on. What's going on is you should imagine it like this. You randomly initialize your network with some choice of theta naught. And then what I'm saying is you just linearize in your parameters that you're doing optimization in the theta parameters around theta naught to first order. Just keep only the linear term. And you just pretend like you use this linear model for the same version of gradient descent on the same loss, blah, 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 blah. And I'm saying even on the level just of the trajectories, the two are extremely close. Okay, so this has a bunch of names. So maybe I should put the names somewhere. So like this is sometimes called the NTK regime. I'll explain what the NTK is in just a moment. This is sometimes called the linear regime. It's sometimes called the kernel regime. It depends who you ask. But the point is that, you know, I told you in the last lecture, a linear model is just one that is, you look for linear coefficients at a fixed basis of functions. So these are your functions. This is the basis that you're really using. It's just the components of the gradient of the output with respect to the parameter, right? All you're learning is basically the values of theta to put here to take a linear combination of these. Okay, so this is a regime in which neural networks become linear models. All the interesting nonlinearity you used to have is gone. So that's both amazing and somewhat unsatisfying, but at least it's kind of a beautiful observation. Okay, so let me just stop for a second to make sure this is clear. My goal for basically the rest of the lecture is I'm going to draw a bunch of pictures and I'm going to explain how to think about this theorem. Okay, and I'll gesture at how it's proved. And really, actually, the proof is not that hard. It's just like somewhat technical if you want to get all of these things to come out. It's more technical than before, if you can believe it. Okay, that's very technical already for me, at least. So I won't do it. I think pictures are better for this. Yeah.
What I don't understand is, then this is the regime that you want to avoid because you want the neural networks to do better than linear models?
Yes.
So that,
But for me, I view it as like this is a regime around which I should do perturbation.
yeah, I understand.
Okay, that's fine. But yeah, indeed. So you might say this is amazing. Optimization is easy in this regime. Neural networks are just linear models. But then wait a minute, I thought neural networks were supposed to be better than linear models. What happened? Well, what happened is you took a bad limit. You know, like that's what I tried to gesture at the end of the last lecture. Somehow, the takeaway is that infinite width networks in this sense cannot learn features. You just learn, you have a fixed basis and you're trying to learn the coefficients at a fixed basis. So, but that means that all the feature learning happens at finite width. So that's why in the next lecture, I'm going to tell you something about neural networks at finite width. But still, it's a place where you can mathematically start.
So the takeaway is that you should allow the depth of the network to grow as well as the width.
That's right. So indeed. So here, I've been very careful to everywhere fix the depth and treat it as a constant. So indeed, the rate of convergence in these kind of results is slower and slower for deeper networks until finally you don't converge at all if the depth is comparable to. That's the kind of point. But okay, this is like we gotta start here. Yeah, but you're right, completely right. Other questions, comments?
Yeah, so the first, like the first claim, is there a limit in n also?
No, M is fixed.
M is fixed.
Yeah,
So is it really zero or is it some epsilon depending on n? I mean, because otherwise it's like every
Here?
function you can approximate.
No, you don't approximate every function. You see the number of training data points is fixed in this theorem. You think of there being 1,000 data points.
Sorry, but n, so there is
But n has to be big.
N also.
See, n has to be polynomially big in the number of training data points.
Yeah, but so is n going to infinity together with t or not? I don't understand.
No. So together with t.
Yeah, it's also.
So this is
T
a
and
uniform
L
statement over t, right? So I'm saying the entire trajectory of optimization for the linearized thing is close to the trajectory of optimization for the nonlinear.
But already the first
This
claim,
one?
is that for n big enough?
Yeah, this is for all n big enough. With high probability, you will succeed.
Equal to zero. Not
Equal to zero, right? And the reason is your loss will be convex. So once it's convex, you're done. Now, I didn't tell you about the rate of convergence, okay, and so on, but yeah, indeed, so I mean exactly what I wrote actually. So somehow when the network is wide enough, your loss is effectively just you see, if you can replace z by z linear, then the loss is simply quadratic in theta. And as soon as it's strictly convex, instead of just weakly convex, let's say, then you're done. Okay, so that's the point.
Yeah,
That's the point. Good. Other questions? Okay, good. Wow. Okay, let me draw a crazy picture. Okay, so I'm gonna spend the rest of the time trying to like interpret what is going on. Sort of wild, but it's true. And hopefully by the end it'll be trivial. Get that in the dream. Okay, so let me draw a picture which is not going to at first be related to this, but then you'll see it's exactly what this actually is. Okay, so how does one prove all these sort of results? Well, okay, so let me go back to my picture I had before. So I have, I can't draw it this way for fun. Okay, this is the space of functions computed by your fixed neural network. Remember that was my beach whale. Okay, my Dolly-esque beach whale. Right, so points on this space are what? A point on this space is nothing more than one of the functions you can get by choosing some value of theta. Right, this is the space of functions over which you're doing optimization. And so you see, I wrote optimization just in terms of the parameters. That's how you typically do it on a computer. But you can think you're just searching over this space of functions. And whenever you search over a space of functions or over something that looks like a manifold, choosing a good set of coordinates is like key to understanding what's going on. And I claim that's really what we've done. Okay, so I claim there's a battle between two kinds of coordinates that you can choose. So the first coordinates are parameter coordinates. That's what I think of them as. They just associate each function up here to the parameter vector that you get. Okay, so this is R number of parameters. And the points in here are just the values of theta themselves. That's one way you could think about optimization. Okay, so let me make a comparison between what happens in the parameter coordinates and the function coordinates. Okay, so I'm going to call these coordinates function coordinates in just a moment. All right, so what happens in the parameter coordinates? Well, okay. So the first thing to say is initialization is easy to understand, right? From the point of view of the parameters, when you start training, all the W's and B's are just independent Gaussian. It really doesn't get any easier than that. Okay, in the function coordinates, okay, what are the function coordinates? It's another set of coordinates. This is like R number of data points. Okay, and your math is very simple. Okay, so what do? Well, I had my training data set. Where did I put it? Of xi's and yi's. And all you do is you send a particular theta to the vector of values of the output at the data points, xi. Okay, so I goes from 1 up to the number of data points. That's the other set of coordinates in which you can think, because notice the function you're trying to minimize depends only on those coordinates. It only depends on the values of the output. Okay, so these are two systems of coordinates. Fine, so initialization here is easy, and here it's hard. Okay, initialization, yeah, I'll say it's hard-ish. So we have to work kind of hard to check, for example, that in the infinite width limit you get a Gaussian. Right? This was really about the distribution of the values that you get. Okay, fine, very nice. Okay, so parameter coordinates are hard for humans. Okay, what do I mean by that? If I just give you the weights and biases of a network, you still have no idea what it actually does. Hard to reason about. They're just a string of numbers. Okay, so they're hard for humans, and they're easy for computers. Okay, and similarly, function coordinates are the opposite. They're easy for humans, that's what we think of in terms of, but kind of hard for computers. Hard for computers. So I'm just kind of explaining the two sets of coordinates, and I'll do something interesting in a second, rather than just saying words. Okay, so now here comes, now I'm going to make two key points. Okay, so here, the loss function L is complicated. Right, so like as a function of the parameters of the network, if I draw the contour lines for L, they're like kind of complicated. Maybe they look like this. Okay, these are like the level sets of L. I don't know. It's some horribly non-convex looking function of theta. And that's the whole problem we're dealing with. We don't really understand why you should be able to drive the loss to 0. Right? But you tell me, what does L look like as a function of these coordinates? What? Huh? Huh? What kind of function is it?
Sum of sum.
Yeah, it's just a convex function. It's just a quadratic function, in fact. Right? It just literally looks like this. It has a unique global minimum, and all of these are equal to all of these. These are literally the coordinates. Okay, not these. Sorry. These are literally the coordinates that it chose. Right? And it just goes out in circles. These are the level sets of L. Okay, so you tell me which function you'd rather optimize. Clearly, you want to optimize this function, right? Okay, so here L is simple. Okay, so good. So it's simple as a function of these coordinates, but you have to pay a price. Okay, and this is where this whole story about the neural tangent kernel and everything is about to come in. Okay, but here, writing down optimization is easy. In what sense? In the sense that I just have a formula. D by dt of theta of t is equal to minus grad theta L of theta t. Right, that was pretty easy. That's how we specified optimization. The reason that it was easy is that these are really my free variables. This is what I get to move on the computer. And so I just move theta exactly as it wants to move. At every point in time, I just go in the direction that L decreases. Okay, so however, over here, what happens when you actually do optimization? Okay, so this is the point. So I'm going to write down the answer. Okay, you can ask what's the resulting dynamics on the vector of z's. Okay, I'm going to write it this way, evaluated on your data set. Okay, I'm going to just give this thing a name. This is z evaluated on your data set. Okay, so at the parameters theta t. So this is a vector. This vector has dimension number of data points. And I'm telling you its evolution looks like this. So yeah, I'm going to write it here so that I don't squeeze it in. So you get a minus sign. And then you get a thing which unfortunately I call capital theta. So I have to deal with that fact, but it's okay. So theta is a certain kernel, which I'm about to write down, which depends on the value of theta of t, times the gradient with respect to just the variables z themselves of the loss function, L of z, okay, at time t. Right down. D. Okay, so these gradients are really the easy gradients. These are these gradients. Okay, now I have to tell you, what is this monster? Okay, so this is a matrix, which is number of data points by number of data points. And okay, it's just an easy calculation to go from here to here. So I'm just going to report the answer to you. Okay, so capital theta at little theta is like this. It's just the dot product of the Jacobians. Okay, it's the gradient with respect to theta of the values on the data set. Theta transpose the gradient with respect to theta, the values on the data set. So it's just the Graham matrix of derivatives that you had on your training data points. Okay, so let me figure out where to put this. Okay, so I'm simply going to erase this. These are useless more or less for us. So I'm going to write down exactly what I mean over here so that I don't have to erase the NTK. Okay, so let me be more precise. So capital theta evaluated at little theta is a matrix. So let me evaluate it at components alpha and beta. Okay, I'm going to fix inputs x alpha and x beta. Okay, so this is equal to, you take the gradient with respect to theta of zl plus 1 evaluated x alpha and theta, and you dot it with the gradient with respect to theta of zl plus 1 of x beta and theta. Okay, and capital theta, this whole thing, is just the matrix capital theta evaluated little theta alpha beta, where alpha and beta run from 1 up to the number of training data. It's number of data points by number of data points matrix. Okay, so let me just put it this way. If you're more like a geometer, doing like optimization in one set of coordinates can be just transferred by understanding how the gradients transform under really any transformation that you want. But you know, the gradient transforms in a covariant way, right? You get Jacobian transpose. You have like a positive definite or a positive semi-definite matrix that transforms your gradients. Okay, so you get this kind of effective evolution equation for the things that you care about. You know, these are the coordinates that humans want to understand. I'm asking, how do the values on my training data set actually change as a function of time? I'm saying they change in a very simple-minded way. There's a positive semi-definite matrix that also depends on where I am at time t, times the vector of gradients that I have for my loss. But this is the coordinates in which the loss has just gone back. So this is a simple set of gradients to compute. Okay, so let me pause for a second because I'm gonna like erase and write some stuff to like hopefully make this more clear. But I want to see if what I'm saying is making sense. Like, should I do this calculation? Do people want to see how that works? Not that bad. Take 5 minutes. Wait, yes,
Can I ask you something?
Of course.
So what we saw yesterday, basically, is that if you have a single layer network,
Yes.
okay, with a great width,
Yes.
basically this is a locally linear function
Yes.
with a lot of aware of changes of
Yeah.
direction. Now, what you're telling us today is that because that would fall under this regime,
Yeah.
you have a single layer with that. In that case, the model is basically linear, but
But in a different set of variables. You see that the function is locally linear, but changing one neuron changes the global values of the function everywhere. It's not actually local. Like where the neuron turns on and off is localized, but it propagates what it does everywhere.
Yeah.
And so it's like it's not linear in those variables about where it turns on and off. But really, if you choose a different set of variables, which is the linearization of your network around the initial thing, then the model becomes linear. So it's like a different basis in which it's like linear. It's like a nonlinear transformation from one basis to another.
it's linear in the functional cortex.
Precisely. So that's what I'm saying. I'm saying like the loss is just a quadratic function of these. But of course, when you change variables, here we chose the metric to be the identity. That's why we were able to write down such a simple gradient update. But when you change variables, the RoMaDS gradient is going to change from just the identity or the nabla with the identity covariance to, whatever Jacobian transpose. That's how gradients transform. And so that's the price you pay. You can either work in these coordinates and use just the usual definition of gradient flow, or you can work in these coordinates where L is simple, but at each point you have a different inner product that you're using to actually compute the gradient. Like the inverse of this is like a Riemannian vector. Okay, so that's kind of the point of this picture. Okay, is that more questions about this? I'm going to say a little bit more to try to make this precise, but people, you need to direct me a little. Like I can do the calculation, but I don't think you'll learn anything by seeing me do it. Just change variables. Okay, I'm going to take that as go on. Okay, so let me state a lemma. Right, so you see let me erase. Talk, right. Look at something precise. Okay, so note what do we have? Okay, so the gradients of the loss are very closely related to the gradients of d by dz. Okay, so what do we have? We have d by dt of the vector of values you compute on your training data set at time t. Okay, I'm free to subtract the vector of labels that I have. Right, because that's constant. This is just the vector of the y's. That's the same thing. Okay, so that's the left-hand side. And now I'm going to write down the right-hand side is equal to minus capital theta, okay, evaluated at wherever we are at time t, this matrix, times, okay, what's the vector of gradients you have? It's precisely the same vector. Right, so this is the equation that you actually get. Right, your loss is nothing more than 1/2 the sum of the squares. When you take the gradient, you just return this vector. Okay, so you get this very simple differential equation. But moreover, you can just take, you can multiply both sides. You can take the dot product of both sides with this. So what do you get? You get the d by dt of the loss at time t. Okay, it's just d by dt of zl plus 1 on your data set minus y. Yeah, I'll write it norm squared. A with a 1/2 maybe, right? That's the definition of the loss. And I just told you what the derivative of one of those pieces is. So, okay, when I take the derivative, I get it over here. The 2's cancel, and what do I find? I get minus. Okay, I get my vector of residuals, CL plus 1 on your data set at time t minus y. Times you get this matrix theta times t. Okay, times you get the same vector on the other side. Okay, so maybe this is yet another way of thinking about what the evolution equation. Okay, so what you see is that the loss is the dot product of this with itself, and how quickly the loss is changing is minus the dot product of this with itself using the covariance defined by this operator, by this matrix. Okay, so this is like kind of the operative equation in some sense. Okay, so in other words, let me write down something that I promise I will stop. So here's a lemma, but this is the way people actually check that the loss goes to zero. Okay, you have a nice differential equation just for the loss itself. And okay, what do you want? You want the right-hand side to be written in terms of the loss. So all you need is you need this to be strictly positive definite. Right? You just need a bound on the smallest singular value or smallest eigenvalue. It's symmetric. Okay, so you have if you know that this matrix of overlaps is greater or equal to some positive constant delta times the identity for all times. Right? Then what do you find? You find that the loss, find that d by dt of L of theta of t is less than or equal to, right? This is a lower bound, but you have a minus. Right? You have minus delta times the loss at time t. In other words, the loss goes to zero exponential. Right? So that means that the loss at time t is less than or equal to x with minus delta t times the loss at time zero. Okay, the lemma proves itself. I don't think you have to prove it separately. Right? So like all I'm saying is if you knew that this thing could be bounded below by delta times the identity for some uniformly positive delta for all time, then because you have a minus sign, this right-hand side is bounded above by what happens when you replace this by the identity times delta. And then you just get the loss back, and that's how you're going to prove that the loss goes to zero. Okay, so this is fundamentally what happens in all the papers that people write in the neural tangent kernel regime in this kind of setup. The game is always, you try to study the NTK and you try to show that it's positive definite. Okay, this is always the thing. If you can show that it remains positive definite for all time, then the loss goes to zero. Okay, so let me just pause for 1 second. Because I want to erase this. I'm going to rewrite the definition of the NTK. And I'm going to try to say something sensible. Okay, moderately sensible. So as sensible as I'm capable of saying. Okay, is this okay?
Just a type,
Yes.
so maybe you need transpose on the detail. Yeah.
Thank you. Yeah, I always forget the transposes. You're right. Yeah, correct. It's just the quadratic form that this induces, correct. I mean, but that's always how optimizing a quadratic function in a Riemannian setting looks like. It looks good, but your metric needs to be strictly positive definite to actually be able to do it. Otherwise, there are some directions you can't move. Then you might not be able to optimize your function. Other questions? Yeah, please.
So what do you mean by delta I? So it's positive definite? Yes, I can follow, but delta I is the identity.
So sorry, I'm saying if there exists a positive number delta,
Okay.
so that in the sense of positive definite matrices, this is bounded below by this, i.e. the smallest eigenvalue of this, that's a symmetric positive semi-definite matrix, is actually bigger than delta. If delta were positive, then you can use this estimate. Well, if delta is zero, this estimate is not very useful to you. And you get this kind of. Okay. Other questions? Okay. I'm going to rewrite this thing. Can I erase? Yeah, I'm going to erase. I'm sorry. I'm going to blame the board space. I need more board space. Or I should be able to write small. I could have planned better, but it's okay. Okay, so let me keep this lemma up for the moment, and let me write down the definition of it. So theta, alpha beta, at a parameter vector theta. It's just a gradient with respect to theta. Alpha plus 1 at alpha theta, dotted with a gradient with respect to theta is the alpha plus 1 of theta. And that's the definition of the Okay, so this thing is called the neural tangent kernel. It's a kernel because it actually takes two inputs, x alpha and x beta, the positive semi-definite function, as you can tell. So it's called the neural tangent kernel, which is not a terrible name, but it's okay. Here is this. So what I'm saying is that there are literally 1,000 papers written about neural networks. Okay, probably maybe 300 papers written about neural networks, all of which somehow prove that optimization is successful in some regime. And the way they prove it ultimately, that's why I left this lemma up, is one way or another, they check this condition. Okay, they check that the NTK, this kernel, this number of data points by number of data points matrix is strictly positive data. Once you have that condition, everything is good. But the question is, how in the world do you check such a condition? Seems kind of complicated. That's what the rest of the lecture is about. Okay, I'm not going to prove exactly how you check it, but I will sketch the proofs of how this works. Okay, so basically to prove this theorem, you essentially just have to show that this holds with high probability under the assumptions of the theorem, and then you're done. Okay, so here's my plan. Let me see how I was going to write this. Yeah, very nice. Very, very nice. This is idea 2. That's not good. 1 second. Where's idea 1? Nice. Okay. Yeah, here we go. Here we go. Okay. So right. Okay, so let me ask you. So there are really 2 ideas for proving this. So to prove this red box holds, here's how you proceed. No, I don't want to do this. 1 second. I like skipped a page somehow in my note. I think it's just gone forever. It's okay. It's okay. It escaped. Maybe it didn't escape. No, it definitely escaped. Okay, it's okay. So okay, fine. Let me explain how you prove this thing. This will be fine. So there are basically 2 steps that people use to prove this kind of hypothesis, the dilemma. And I'll explain how to do both of them, essentially, at least in a very heuristic way. Okay, so step 1 is you say, well, I'm going to study this matrix at the start of training. Okay, and I'm going to say this is greater or equal to delta times the identity with high probability by using some kind of generic matrix concentration. Matrix concentration inequalities. And I'll show you in a simple 1-layer case why that should be. Okay, so I already told you a lot about how to study wide neural networks at the start of training. We didn't exactly talk about the derivatives, but you can study them in essentially the same way as we study the values. And step number 1 is to say, okay, at least I want to check that this is true at t equals 0. Phenomenal. And then step number 2 is to say, okay, if you know that this thing is positive definite at the start of training, so then show that this matrix of overlaps for the derivative doesn't change too much. Show that the sup on t greater or equal to 0, okay, of this matrix at the start of training minus this matrix after time t. Let's say the operator norm is less than or equal to delta over t. Okay, again with high probability. With high probability. Okay, cool. If you start well conditioned and you don't change much, you stay well conditioned. Okay, that's the outline of every proof ever known to mankind in this regime. Okay, so the rest of what I want to do is I just want to give you a little bit of a sense of how one can actually check these things. Okay, this is clearly a strategy of proof, but why should this thing be like a positive definite at the start of training, and why should it not change too much? Okay, you see the fact that it doesn't change too much, as I'll explain a little bit more in like 5 or 10 minutes. You see, the NTK is just about the first derivatives of the network. So the change in the NTK is going to be about how much the first derivative changes, in other words, the Hessian of the network. right? The derivative of the first derivative is the second derivative. Yeah, that's true. So what we're going to show is actually that the Hessian of the network gets closer and closer and closer to zero, which is of course what this network is saying, right? If you just Taylor expand your neural network around the start of training, you could continue to write, and your next term would be like the Hessian, and you have the third derivative, and you have all these derivatives. The fact that you can drop the other terms is just saying that the Hessian term, for example, goes to zero, right? Your network becomes linear. So these two things are related. Okay, so let me say something concrete. So let me give you some intuition with one layer networks. Okay, so let's do one layer networks. All right, very good. Okay, so okay, we can be very concrete here.
So now you're on point two.
No, I'm going to explain both for the case of one layer network. Okay. Right, and they're both true for arbitrary depth. Just the proofs are a little bit more painful. Okay, so I'm going to change a little bit the parameterization I have for my network, but it's going to look like this. Okay, so it's this. I'm going to turn off the biases because it doesn't really matter. They're just a nuisance essentially. But I'm going to put the 1 over square root of n's out in front of my weights. I'm going to take the weights to be order 1 and have this scale of variance. Okay, W2I sigma of W1I times x over square root of n naught. Okay, so remember, usually at the start of training, the variance was like 1 over the width, but now I'm just going to take these to be like order 1 random variables because I've taken the variances out. Okay, I've changed the parameterization a little bit. Okay, so here's what I want to show first. Let's compute some derivatives. Okay, we're actually going to do it. Let's compute the NTK. So it's not so bad. Note. All right. So let's compute the gradient. So if I take d by dw, what do I do first? Okay, 1i of the output at a fixed x. Right. This is the kind of thing that goes into this Jacobian. What do you get? Okay, well, it's very simple. You just keep that 1 over square root of n in front, and you get that particular W2, and then you get sigma prime W1I times x over square root of n naught times x over square root of n naught. Okay, it's not too bad. I'm just saying you can explicitly compute these derivatives, but something beautiful is going to come out. Okay, I promise. So now I'm going to compute d by dw2i of z2 of x and theta. So what do I get? Okay, now when I compute the derivative with respect to the second layer weights, I just get this term to come out. So I get 1 over square root of n1 times sigma of w1i. Thought it was x over square root of n naught. Right, so I've just computed all the components of my Jacobian. I just wrote them out for you. Okay, very nice. So what does this show? So now let's actually write down the NTK, or a component, let's say, of the NTK. Okay, at some vector theta. So okay, I'll do it at theta naught because that's what I'm supposed to do in part 1. So let me take this at initialization. So what do you get? All right, so I have the 1 over square root of n's here, and I have to take the dot product of a vector with 1 over square root of n's and a vector with 1 over square root of n. So I get a 1 over n out in front. And then the dot product is going to ask me to sum up over all the w's, w2s, and all the w1s, right? The product of these things. Okay, nice. So what am I going to find? I'm going to get the sum on I goes from 1 up to n1. So when you take the derivatives with respect to, let's say, w1, what do you get? You get the w2i quantity squared. And you get these sigmas, right? You get sigma prime of w1i. I'm being hopelessly explicit. But okay, I don't know what else to do. You just get a thing. Even I can write it out with all the mistakes I make, so anyone can do it. Okay, that's what happens when you take the dot product of just the derivatives with respect to w1s, right? Plus you need the w2s. Plus you get sigma w1 I x over square root of n naught. Then alpha sigma w1 I x theta over square root of n naught. Do you agree? right? I have to sum over all the parameters in the network, the derivative of like the output with respect to that parameter at x alpha times the derivative of the output with respect to that parameter at x beta. So I just use my two formulas above. Okay, so what's the point I'm trying to make? Okay, so this again, audience participation moment. Okay, what is good about this thing? Remember, the WIs are IID, they're order 1 random variables. The W2Is and the W1Is, they're all order 1 independent random variables. What form does the NTK take? Well, I mean, it's not necessarily diagonal. I mean, the x alpha and x beta are the coordinates for it. There's going to be some sort of matrix, but like, what's the structure of this matrix? Okay, what can you say about circle something? So, okay, this is the thing of summing. This is the function of I of something. What can you say about the thing in the yellow brackets for different i's? At the start of training, right? I'm at theta naught. Okay, they're independent. Right? In fact, I would say they're IID, wouldn't you say? I think I would say. So you see, the NTK is just an average of IID random matrices at the start of training. Okay, each component of the NTK is an average of IID things. So the whole matrix is just an average of IID matrices. And that's exactly the kind of thing that you apply matrix concentration to. Okay, so that's the point. So this is an average. So the entire matrix capital theta naught is an average of N1 IID matrices. Okay, and matrix concentration tells you that with high probability, this is very close to its mean. Okay, so all you actually have to do is check that on average, this thing is positive definite. And that's not too bad. That's not too bad. That's something about the particular properties of the nonlinearity that you have. You have to actually work to do that in every specific case, but it's pretty easy. Okay, so the point is that just like we saw in the first half of the lecture, this is like a collective observable, right? It's the sum over all the neurons in the first layer of the same function applied to things that happen only at each neuron. So these things are self-averaging. They're going to be close to their mean, and then you have to analyze the mean somehow. Okay, so that's what I mean by this first step. That's how you check things at initialization.
For instance, in the ReLU case,
Yeah.
the sigma prime is either the 1 or 0. Right?
Yeah. So, but like all you have to know is that these are bounded random variables, or sub-Gaussian, whatever you like. Right? These are order 1. Like think of this as Gaussian mean 0 variance 1. Right? As long as sigma prime is like polynomially bounded, like all of these are polynomially bounded things, so they have all the moments you could ever hope to.
Also, the second bit is either the square of WI1 or 0.
Yeah, correct.
So in that case, you can really compute.
Yeah, you can compute everything explicitly in this context. That's right. But somehow the point is, no matter what nonlinearity you put in here, it's very generic. As long as these are order 1. Like I'm saying, the same kind of thing happens for deeper networks too. They're not literally IID, but they're going to be sums of weakly correlated things, and you'll still be able to say it's very close to the mean. That's the point. Okay, so that's how you check things at initialization. When the network is wide, you just get an average of independent things. You compute the mean is positive definite, and then you're pretty happy. Good? Okay. Very good. Okay, so I have just enough time. Let me tell you how to do part 2. Okay, so let me erase this and keep going. Okay, so something very magical happens with the Hessian. So let me erase this. I'm going to do it for a very particular reason. Okay, so let me say what happens in part 2, and then we're going to do the calculation and see why this works out. It's going to be nice, I hope. Okay, I think it's nice. Okay, so here's the point. This is the thing that I want to bound. So how am I going to bound the yellow box? Okay, well, the only way I know how, right? This is less than or equal to the integral from 0 to t of the norm of the derivative with respect to t of the NTK. Maybe with respect to s at time s ds. Right? You use the fundamental theorem of calculus. Not too bad. Now, the derivative of the NTK, right? The NTK is just the Jacobian transpose Jacobian. Essentially has the following form. This looks like the integral from 0 to t. You get the Hessian with respect to theta of the network that you have at time s times the gradient of the loss at time s ds. That's the form of the integral you get. I'm being a little sloppy, but I'm just saying the first derivative with respect to s of these first derivatives, you just have to differentiate the theta. And so one of these will become Hessian. You'll have the second derivative. That's the form of the estimate that comes out. And what I'm about to show you in this one layer case is that the Hessian, okay, and the norm of the Hessian of your of the output, CL plus 1, looks like this. It is, okay, it's less than or equal to some constant that looks like this. It's going to be polynomially big in the number of data points. And it'll go to 0 like 1 over the square root of the width of the network. Okay, so that's what we're about to see in the one layer case. In order to say that the NTK doesn't move much, you're going to say the movement of the first derivative is controlled by the Hessian, and the Hessian is extremely small. Namely, if you fix the number of data points you have, and you take the width to be a polynomial in the number of data points, you can make the Hessian as small as you want. Okay, so then the change in the NTK is as small as you want because the loss is going to go to 0 once the NTK is positive definite, blah, blah, blah. Okay, so there's some kind of, okay, so that's like the idea for doing this. So now you tell me, let's see what happens. So let's see. Very good. Good? Yes. Nice. Okay. So we computed the first derivatives. So what I'm saying is what you really need to convince yourself of is that the second derivatives of the network are small. So let's see what happens. Let's compute a second derivative that looks like this. D squared by dw1 I dw1 j of the network output. So what do you get? What do you notice about, so let's take the derivative with respect to w1 of this thing. What happens? Something, do you see anything? Okay, let me give it away. So you see here, when I took the derivative with respect to wi, only wi's survived. Okay, so when you take the derivative with respect to weights of different neurons, you get 0. So you have a delta ij. Okay, so the Hessian is going to be block diagonal. It's only going to know about things within a single neuron. And moreover, it's going to have a 1 over square root of n1. Take times some stuff that's order 1. I'm just going to write it this way. I'm going to spare you the details. Okay, similarly, the same is going to be true if you take, for example, the second derivative with respect to w1i and w2j. Okay, it doesn't matter. The only w2 that appears here is the w2 from the same neuron. Okay, so again, this is going to be delta ij, 1 over square root of n1 times something that's order 1. Okay, and the second derivatives with respect to the w2s are just 0 because the thing is linear in w2, so it's even better. Okay, so what's the point? The point is this, that the Hessian of your network with respect to theta, with the Z2, has the following structure. It's just a block diagonal matrix, H1 down to Hn1. It's the number of neurons. Okay, where Hi is the Hessian with respect to theta, sorry, with respect to just the weights of the one neuron, Wi and W2i of the output. Okay, so this is just a like fixed dimensional matrix. The dimension of this matrix is input dimension plus 1. Okay, these are bounded blocks, each of these blocks. And the form it has is it looks like 1 over square root of n times something order 1. 1 over square root of n1. Okay, so you see there's a sparsity that's hidden within the neural network. Namely, the Hessian is actually sparse. Most of the entries of the Hessian are 0. And it's just a block diagonal matrix with bounded blocks, which are all uniformly going to 0 as the width gets bigger and bigger. Okay, so that's why the neural network becomes similar to its linearization. You could just Taylor expand this as far as you want, but all the higher order terms go to 0. Okay, the gradient remains order 1. If you take the sum of the squares of this thing, you're going to get 1 over n1 times the sum of the squares of these guys, and that's going to be an order 1 thing. It's going to be an average of I and n variables again. But the Hessian goes to 0. So if your gradient stays order 1, your Hessian goes to 0, you become linear. That's the definition of linear, right? The linear is you have a Jacobian, but you don't have a Hessian. That's at least what I teach my students. And so you see, that's why the NTK is not going to move too much. The movement of the NTK, it can only move insofar as the Jacobian of the network can move. But the movement of the Jacobian of the network is controlled by the Hessian, which is itself becoming as close to 0 as you want. And so that's kind of the circle of ideas that gives rise to all the proofs around this kind of like analysis. And different people parse it in different ways, and they get more precise, less precise, whatever. But that's the basic point. Okay, so I like this one layer example because basically you see that like the neurons, they get collected at the output and they all contribute to the output, but somehow like the mixed derivatives don't really know about each other. Every neuron acts like its own thing on the level of the Hessian. And every neuron only contributes 1 over n to the Hessian, roughly speaking, right? There's n neurons and each one of them contributes something on order of 1 over n. Okay, good. So let me pause. I was going to say something else, but I have like 0.31 seconds left. So are there comments or questions about this last thing? I tried to at least give us some sense of how this works. But I feel like I really crammed a lot into this lecture. I don't know if that's good or bad, but probably somewhere. Questions, comments? Okay, so I'm going to stick around. I'll be happy to take people's questions offline. What I'll do next time is I will not talk about training anymore. I'm going to go back to talk about initialization and how you study networks at finite width. That we saw in the first part of the talk, and this second bit here, somehow neural networks at infinite width are almost trivial. There's not much there for you. And so you have to do something that breaks you out of this regime. There are many things you can do, but I'll tell you how the finite width thing breaks you out of this regime.
I have a stupid question. So this approximation here becomes worse as theta gets away from theta 0, right?
Yes.
How far away does it go?
Well, the thing is, it doesn't go too far because you see, at the start of training, you're positive definite. So by the lemma that I wrote down here, your loss starts decreasing exponentially fast.
Okay,
And so you only have so much juice to go. And that's kind of how the real proofs go. You start decreasing exponentially quickly, which means theta doesn't move much. But if theta doesn't move much, then the Hessian stays close to 0. And therefore, the NTK doesn't move much. But if the NTK doesn't move much, you're still positive definite and the loss still big. It's an argument like that, which you have to make precise, but that's the point. So the point is that the total, that's why you get to control the total trajectory. It's because the displacement is actually very small. Yeah, please.
Sorry, maybe a silly question, but how do you control it for the yellow box, the growth in T?
Yeah, so again, the growth, you control the growth in T because the gradient of the loss goes to 0.
Oh.
That's why I wrote this thing in. Again, the heuristic is you start off as positive definite with high probability. So by the lemma I erased, the gradients of the loss start to go to 0 exponentially. But if the gradients of the loss give you integrability in this thing, then theta didn't move too much. And if theta didn't move too much, then the Hessian remains small, and therefore this thing remains positive. Okay, it's like it's some kind of, you have to do some kind of continuity method.
Same question as before, but just in terms of like a trivial interpretation. If the basic message of neural networks was that to over-parameterize was not such a big a problem, now you're telling us that it is a problem if you have a single layer.
Well, what I'm telling you is that so I'm sketching one way to show that the loss goes to 0, which is to say the NTK remains positive definite. But the NTK could remain positive definite and change a lot. It's just no one knows how to show that. You only know how to show that it stays positive definite. If it starts positive definite, it doesn't move much. But this is very sad. Very, very sad. but that's the way.
So in this sense, you can layer it is indeed a problem over parameterization.
Well, the point is how much overparameter. Like what the thing in practice is that you need enough overparameterization for the NTK to remain positive definite. Remember, I told you that this matrix here, like the NTK should be positive definite because like you have way more parameters of training data points. So you need enough parameters for that to happen. But you don't want so many parameters that you just reduce to a linear model. So you need big networks, but not infinitely big networks, is like what I would say. But that's what makes it interesting. So sweet spot. It's a new trade-off. Okay, it needs to be given a name.
But for what you told last time, yesterday, for one layer, so one layer neural network, at least you are always linear, locally linear. You are just doing linear model. That's the point.
So
One-
only if your width is much bigger than the number of training data. That's so
You are in over parameterization regime.
So the point is over parameterized is
Over.
yeah. So there are many ways to be over parameterized, and if you're too over parameterized, you're a linear model. If you're less over parameterized, what happens in practice is optimization still succeeds, but you're not too close to a linear model yet. So if you don't have enough parameters, you won't be able to optimize. Too hard, your function L does not come back.
Okay.
If you have an infinite number of parameters, then you can optimize, but it's pretty sad. You're just a linear model. Why not use linear models after all? But in the middle, something interesting happens which you just don't understand. And that's where sort of in some sense the mathematics is like, that's why this is just a starting point from my point of view. It says, okay, now I understand what happens when I have way too many parameters. Everything is very analytically tractable. Now, like, how many parameters do I need to keep the NTK positive definite without keeping the Hessian too small? That's the kind of
Bias and variance trade-off from statistician point.
exactly. It's not like bias and variance. It's more like tractability and like versus feature learning. Like you want like the complexity of optimization to remain low. You want to be over parameterized enough that optimization is easy. But you don't want optimization to be so easy that you are effectively a linear model.
Because you say, since you interpolate your data, you are always by zero bias.
Precisely.
And so the problem is not bias in variance trade-off. but
That's right.
And
Exactly. There's no bias anymore, and the variance
Yeah.
keeps going down. That's like what the thing that people draw with this double descent.
yeah, double descent. So that's the.
But actually, double descent is a bad picture. Okay, so since
It's always
you asked, okay, I can't help myself.
yeah. But now
Let me draw one thing, and I promise I will stop. Okay. So like, yeah, I can't help myself. You're asking a good question. So you can plot on here the number of parameters in your model, and here you can plot the error you make on unseen data points. That's the usual thing people do. And here's going to be the number of data points, roughly speaking, that you're training on. So fix the number of data points. Consider taking bigger and bigger networks, roughly speaking. Okay, so when you have way fewer parameters and data points, you get the usual bias variance trade-off. And then often what happens at this interpolation threshold is the variance goes to infinity. You're as ill-conditioned as you want, and the bias is whatever it is, maybe it's 0. Okay, but then what happens, this is what people typically draw for double descent, that it starts going down again. Right, and this is saying, when you have a lot of parameters, actually, like, the bias is already 0, but the variance actually is low. But this is not actually the truth. Like, people lie to you, just like I lie to you, but I lie less. So what actually happens, in many interesting cases, there's another bump. So maybe it actually looks like this. Okay, there's a regime where you're over-parameterized, but not too over-parameterized. Where something really great happens, and when you're basically infinitely over-parameterized, okay, yeah, you fit your data, but like a linear model. You don't do that well. So it's like, okay, multiple descent, triple descent, okay, I don't know. So somehow, like, this is the classic picture, and the thing I erased is kind of the more or less naive picture. But even for like interesting random feature models and this and that, like you get this interesting kind of picture. So it's more complicated, and really describing what's going on here, even proving that this happens for neural networks is open. But people can show this for simpler models.
and when you go deep, and so when you go deep,
Yeah.
so you make L
Yes.
go. Are you still doing the linear model when you
No.
no?
So here, okay, here's the
Here,
So if you look at the Hessian, right, so I told you that the Hessian looks roughly like this. It looks like square root of the width. But actually, after L layers, it looks like square root of the depth of it. So as soon as you're comparable depth and width, now you're not close to a linear model even at infinite width, nor are you a Gaussian process, as I'll explain next time.
So that's why people go.
So correct. That's one way of interpreting what depth buys you. It pushes you away from the linear regime. Yeah.
Excellent.
So maybe I should have said that, but okay, I couldn't help myself. I said this. Okay, you asked all the questions.